Yes, we are live.
Okay. Oh wait, I can video file. No. Just a second. Okay, so this is a video that Vet made where a rover is being controlled by an LLM. Just a second. He didn't ask me about.
Of my YaRG rover driving LLM
Do you hear the audio?
Yes.
application. We've talked about a little bit in chat. The idea here was to wire up GPT-4 vision and see if it can actually help operate a rover. I've got a lot of interesting aspects to this and some successes and a lot more failures. But let me just give a quick tour here. So what you see before you is the system message for the rover itself. And I've tried to give it a sense of having a position in the world and how to act. One of the strange aspects to this application is that because GPT-4 Vision doesn't really support function calling all that well and doesn't really do everything as well as normal GPT-4. So I'm trying to actually use two models and have them communicate with each other. And that's the concept here of this agent called eyes. And so what the rover can do is it can call functions such as going forward and going backwards and going left and going right. And then it can also call a agent called eyes and ask it to describe or look around and get some description of what's going on. And then I have some strategies here to help it kind of interpret that information that it gets back from its eyes and do something with it. Whether that actually has worked very well, I'm kind of skeptical of. Here's the system message for the other agent, which is the eyes, which tries to give it some perspective on what it's seeing outside of its like viewport, so it can kind of know where in the image what it means for something to be, you know, at the very bottom of the image and in the front, to try to give it some guidance on whether that would work. I very quickly.
I just wanted to interrupt here and say that basically it's two LLMs happening at the same time. So it's like a right hemisphere and a left hemisphere that we talked about.
Realized that it wasn't doing a very good job of being able to relate objects in the viewport to like know where they were. And so I tried an experiment of adding an overlay to where we could put grid lines and say like, here's how many degrees from the left to the right, and to get that to allow it to better describe where things are in space. I don't really think that that's worked super great either, but well, it's interesting to see. The program itself is written in Go because that's how I love to do things. You can see I've got this the system here where I add some functions called forward, back, right, and left. How this is architected today is that we are actually calling the rover's API. If you remember a previous session where we talked about the YaRG API, it allows gives us a web API to be able to communicate with the rover, so I can post commands to this URL, and then it can run the rover and move it forward, move it around, whatever. And then, yeah, so then we're doing some image overlay stuff. So it's grabbing an image, again, from the URL here. It can download whatever the current image is, and then we're overlaying this grid on it that gives it some space, and then you'll see some examples of that. starting up the project here. We've got a command line application with some kind of niceties for working on the console. It looks kind of pretty. And over on the right, you can see I've got a camera set up where we can see the rover in space, the play field that we're dealing with. The rover's down there on the left, and then we've got a target of a Baby Yoda doll up in the right. So then we can give it some instructions, a little mission that it can pull out or it can run, and we'll see how it does.
The mission was
the first thing it does here is start the agent so it can talk to the camera. The camera gets an image, which we can see displayed here, and you'll see these grid lines that are on it. So we can see that the Baby Yoda is off to the left about negative 10 degrees. However, look at the response that we got back. That is not at all correct. The other error you can see here is if you look closely at what the assistant said, it actually tried to complete its own description of what was in front of it. It asked the eyes about stuff, and then it also answered it. So there's some issue with how this pattern of communicating with an agent where it's trying to role play also the response sometimes. And I don't quite understand why that is or how I can stop it. But ultimately, the agent does respond, and well, the result is also incorrect.
I don't know. It seems to be getting. Oh, no.
Let's give this another go. Same basic setup, and you can see a different failure mode that we didn't see in the previous one.
So it says align yourself with the doll and get closer so you can get a better look.
This is an even worse version of the hallucination. It may be more clear. It says like, so can you tell we're in location in relation to our current location? And it says, and then it completes its own sentence and says, sure, scanning now. I see a Baby Yoda doll. It's slide to the right about 15 degrees. I don't know how much that actually ends up influencing what the eyes actually says, but the eyes is also wrong. It says it's 5 degrees to the right. Of course, neither of them are correct. It was actually to the left. Sadly, the rover decides to go with that, turns to the right a little further, and then moves forward. I think in this case, it actually instigated a hallucination in the eyes. It got it to say that there is actually a Baby Yoda doll ahead, but there clearly is not one. Now our rover thinks it's done. Obviously it's not, but then I just tried to think of what else. Can we get it to convince itself that it's not correct?
We are now closer to the
so
Baby Yoda doll.
Describe what it's seen. And again, the assistant tried to describe what it's seen before, like it just hallucinated its description of what it's seen. It thinks that there's a Baby Yoda doll in front of it, so it said, I see a Baby Yoda doll. But what do the eyes actually say? The eyes give also a bit of hallucination, indicating that there's a Baby Yoda doll there. And but then the assistant gets even more confused. So it finished talking to its eyes. It comes back to the user, but it doesn't actually realize that it did not relay all the information that was asked from the agent back to the user. And so this is totally an artifact of this somewhat strange interaction model that I'm using of having two LLMs talk to each other. They're just not quite there, but requires more experimentation, perhaps.
There is no grounding to what is happening in the real world.
It kept on saying it saw a Baby Yoda doll.
I don't think it actually saw it. I got the impression it was pretending to see it, right? It was pretending to see it.
It could be that it doesn't know what a Baby Yoda doll is, and it saw a shadow and said, oh, that must be a Baby Yoda doll. I don't know. But it identified it on the right and it turned to the right.
Yep.
Okay. So
But you actually like I don't know how this is going to work, right? Because you don't actually need eyes to move, to have the affordance of moving to that direction towards the doll. You don't need vision. You basically can like, let's say if there is a gripper, and then you can just program it so that it moves and grabs something and feels a certain affordance, and then you can basically program it to go to left and right. It just needs to understand left and right with respect to its body, and you don't need vision for that. Yeah, vision helps.
yeah, but
This is like
we
a
want.
human machine interface. This is not actually like the robot knowing what it's doing.
Why do you say that? He gave it a command, find the Yoda doll and go towards it. And he had one LLM saying what it saw in the image, and the other LLM deciding what to do and giving commands to the rover. That wasn't doing anything except for giving the original command. Only problem was that the rover maybe it got right and left mixed up, except that it identified the Baby Yoda doll in a picture which didn't have a Baby Yoda doll anymore.
What was the camera used? It seems like the oak tea, right?
Don't know.
Yeah, because to sense distance, you actual distance, you need stereo.
But it still said it's about 2 feet away.
That is
No, I
just the
mean,
guessing.
that's why he overlaid a grid on the image to give you the angles and maybe
Yeah.
also to give you the distance because
No, you don't get the distance without stereo. You need the
you don't
stereo
need.
disparity to calculate the distance.
Let me explain. If most of the area is flat and you project a grid line on it according to the angles, so a line tells you the distance.
No.
Not the line where it crosses the object. The line where where the object touches the ground. Imagine you're looking at a tiled space,
Yeah.
okay, and you have a person standing there. You don't look at where the head of the person intersects with the tiles. Look where the feet intersect with the tiles, and then the person is standing at the distance according to the number of tiles. And that's what he did. I don't know if ChatGPT
So
can
you can
understand.
get the ratio, but you can't get the actual distance.
Why not? He knows how tall the rover is and what the field of view is. He can know exactly how far an object on the ground, on the flat ground, is from him.
No, you just get the actual ratio of the distance, because you need some sort of real distance. So what stereo camera does is uses the distance between the two cameras and the angles, and then there is like a disparity
No.
factor you get, and with that you multiply it, and with since you have the actual distance between the two cameras, you get the actual distance.
Yeah, but here we know how tall, how high the camera is above the ground. So we can map each
Yeah, so
pixel.
this basically that is like using the, yeah, kind of, yeah.
Yeah, but there's a few
Yes,
assumptions here, okay, which
yes,
won't work
yeah,
in
yeah, yeah,
Mars, but they'll
yeah.
work in Let's Garage. I don't know. I think this was very interesting, and I hope Red is wrong about the LLMs feeding hallucinations off of each other, because we really need to fewer hallucinations to get around in the world. What do they call it? Reality bites back. So, well, we don't want that to happen.
I don't think that's going to be a showstopper, because this seems to me a specific example of retrieval augmented generation, where the RAG approach, and except instead of looking up sources online, it's looking up sources in the real world through the camera.
Yep.
So that's not hard to figure out, or not a showstopper. But I think the part that's still uncertain in my mind is this could be a dead end architecture, because when I think about how biology does it, there's two basic ways biology solves problems like this. One is, if precision is required, it actually just decides this is a problem where you need to do measurements and calculations, and we as humans, the only species that can do it, we kind of like just switch into engineering mode. We take measurements, measure angles and distances and so forth. The other way is trial and error, and training muscle memory on like very location specific things, like a
How would
lion
be?
that's hunting a baby Yoda type prey. It'll try enough times and it'll realize that if it looks this small, I have to like run towards it. If it's this small, I can swipe at it, right? And I would say all species other than humans basically learn through trial and error, depth of field and distance and orientation and things like that, which means they can get easily confused if they see completely unfamiliar things at distances where the stereo vision doesn't do much good, right?
Yeah. Well, I read a very interesting article which was talking about our vision and our sense of touch. And basically, babies learn to make sense of the world according to what they can reach and touch, and that helps organize what the visual field means.
Yep.
So yeah, the
It's
rover
like
can do that too.
it's like the neural network in the body of the baby trying to uh, recognize the affordances within its like influence or like the body reach, and then correlating it with the vision about how the actual affordance works. So, but like even if like you don't, if the baby is not able to see, the baby will be able to grab something. It doesn't like there is no need for vision.
Right.
And there's a lot of like objective. I'll share this image from a blog post of mine that might be interesting to talk about here. Share screen. Hold on, where is this? This one. Yeah, I was thinking about like embodiment in robotics. This is from a blog post called Beyond Hyperanthropomorphism. And this is my attempt to map the visual field to like regimes of processing. So I called what we just talked about manipulable reality. So
Yep.
stuff where your reach and vision are the same, and usually are useful parallax distance is about the same, right? Our after babyhood, our near vision, what I forget what that thing is called. It's about 25 centimeters. That's the closest we can focus, and then relaxed is infinity. But in this between 10 to the power minus 3 and 10 to the power 1 meters, we kind of like can grab things, rotate it. They tend to be small. We can take an apple and rotate it very close as dust on glasses, and that can create weird optical illusions. But the next zone is what I was thinking of as perspectival reality, where typically you'll need to recognize what the object is in order to kind of like guess how far it is. Like if it's a tree, then it's sort of like subtended angle will tell you how far it is. If it's a building, it's something else. And here also, I think you can have weird optical illusions because parallax is becoming much less useful here, I think. I forget what I meant by stereo reality. Yeah, things that are at the distance of approximately clouds and horizons, but I've forgotten what I said about it. But then there's kind of a dead zone where we really think mainly in terms of concepts, because there's not much at that distance in our normal visual field, right? Like we can see maybe high altitude airliners or something, but that's it. But then there's a distance at which reality is basically flat for us, like our parallax is not good enough. And mainly that's the sky, I think. But even that's kind of interesting because it is used in navigation. I read about species of spider that orients towards the moon. Have you guys heard of that? It's sort of
No.
like, yeah, yeah, I'll see if I can find it. But yeah, I think the basic solution, they're called jumping spiders. The basic solution is to have a multi-setting, a multi-regime way of processing visuals and making highly leveraged use of what you recognize the object to be in order to do ranging and other like size and distance calculations. So this is why you can like I remember one this was in a short story or something. The character sees a bug on a very clean pane of glass, so a very unfamiliar kind of bug on a very clean pane of glass about 5 meters away. But because they can't recognize what kind of bug it is, they think it's like a 10-meter monster that's like hundreds of meters away. So that always struck me as like the importance of recognition in sort of vision computation. So if you've never seen a bug before, you can think it's a monster like a dragon, kilometers away, which could be a problem on Mars, where the landscape will be kind of like unfamiliar and very scale free, like a big rock at a small distance versus a small rock at a low, short distance. Yeah, this is kind of interesting. I forget how they do it, but yeah, paywalled. All right. Yeah, this was an interesting experiment. I'm also curious about how we could run another experiment, which is suppose we did in fact have a specialized exact ranging and navigation vision module that does like a more normal GoFi style computation, which is take like a laser rangefinder, angle calculations, and do like normal engineering things, objects, angles, recognition, segmentations. How would you integrate it with an LLM for a control loop? Like, would it like right now? I think GPT can basically make a decision that something needs more math and fire up a Python module and do some calculations, right? So
Yep.
we need that kind of interface for interfacing with like a we could call it like an intelligent vision accelerator or something.
Or it could be just basically a small web server running on the robot with a REST API, and then the GPT could keep on querying the API. Okay, what is the distance of that, or what is the distance of this? Uh, Something like that.
So the web server would be the interface to the camera, or the camera would be separate thing that's submitted.
Yeah, it would be an interface to the camera, yes,
Yeah, that's
or the robot itself. Yeah, doesn't matter.
Hmm.
yeah. My instinct is that you will need a specialized sort of vision geometry thing because, I mean, we are basically LLMs or LAMs or whatever. And anytime we have to do precise things, we do the same thing. We bring out specialized
No.
instruments and measure and stuff. Like,
No.
what do surveyors do for building roads?
When was the last time that you played baseball and started using surveying
Yeah,
systems?
but that's not the use case I'm talking about. I'm talking about like more precise navigation in unknown environments and stuff.
How precise? That's what I'm saying. When you walk around a city you're not familiar with, you never take out your surveying equipment.
That's because the landscape has already been surveyed and there's like signage and number of kilometers, things like that. Like if I see a sign,
No, but when you walk around in the fields, okay, when you walk on a mountain, when you go on a hike, your sensory estimation of distance based on your past experience, which is exactly what GPT Vision has, is good enough for you to get close enough in order to do another iteration of the loop.
I think that's like very local actions. I do use maps. I do like pull up Google Maps. If it's like a long way to the next rest stop, I make sure I have a water bottle. So there are like there's multiple levels here, but I think for anything sufficiently complex, we do use specialized tools. We don't do trial and error, winging it for everything. Like if I'm going on a long drive, I make sure there's enough gas in the car.
But if I'm going from one Polynesian island to another one, I don't have a map like Google Maps. I just have way markers.
Have you seen Polynesian wave navigation stick charts?
Yes, we saw it. It's very complicated.
Yeah.
But it's not Google Maps. It's
No, but it is memorized. It's precise. The navigators kind of memorize the particular journey they're going on. They don't take it on their journey, which is kind of interesting. They memorize the stick chart and what it says, and then they kind of know it. And the trial and error, I think, happens at doing the same voyage multiple times, and then you've kind of trained your muscle memory to do that particular voyage, maybe. But there's also there's celestial navigation. How do you find where north is? That's a fairly precise astronomical orientation thing that most of us know how to do. Like look for the pole star, that's north. That's like a within 1 degree kind of orientation mechanism, right?
Right.
And people know a little bit more astronomy, we can do a lot more. But okay, fair enough. It's some mix of like trial and error, dead reckoning, and precise dead reckoning, and specialized instrumentation and stuff.
Okay, I never knew about these things. This stick chart.
Yeah, I first saw them on a vacation in Hawaii. Our hotel room had one of these, and I was like, what the hell is this? Is this a nice piece of art or something? Then I found an entire book about it. These are really clever. It's like they capture how waves refract and swell around islands, and the way the navigators detect them is they lie flat on their stomach on the bottom of the canoe, and they actually feel it in their gut, like how high the waves are going or which direction the waves are coming from. And they also use, I think, a little bit of astronomy, where they're like some stars tell them like some orientation. Yeah, I tried to actually learn this at one point. It turned out to be too hard.
Yeah, but you should make your own candy wrapper charts for using in navigating LA. Well, you're not on LA anymore, but we shouldn't be using sticks. It should be different. The patterns of traffic.
Yep. There was... that makes me wonder what's the sort of like native and natural navigation representation for robots, assuming it has a camera and maybe one of those ultrasonic distance sensors. What is the natural way to do it? So ultrasonic distance sensor makes it like a bat sonar type thing. So that's a very different paradigm than that's like, I guess, input into SLAM and traditional robotics. Actually, can you navigate without SLAM in an unknown environment where there's long range point A to point B, and do so efficiently, like as well as like SLAM is what it gives you something. I think the algorithm is D star. It's like A star, but where your map is being built up over time. So it has some optimality properties. But I think if you just fumble around without any graph search, it'll be pretty bad. But yeah, it would be interesting to see what's the LLM equivalent of SLAM.
Let's take that a little bit further. Are you talking in general, or are you talking in the context of a rover?
I think kind of general, because I don't use SLAM when I'm like learning an unfamiliar environment. I do more like landmark.
No, I understand, but I'll explain my question. When you say SLAM for LLMs, you could be talking about how LLMs explore concept space. But when you talk about rovers, in a rover, when you do SLAM, you shooting a LiDAR and in different directions.
Yeah, so I'm talking
information
space, not conceptual space, because physical space is orientable. There's a direction. So
so I think Vet started with that.
Yep.
Okay, Vet really showed us that when you send out your LLM beam, what you get back is a bit jumbled. So the question is, if I take one LLM image and another LLM image, in a SLAM system, there would be some type of integration. And in an LLM system, it's a total mess. So we don't know yet how to take two images side by side and put them together so we get a picture. Imagine that rover spinning in space 360 degrees. Okay, so if it was a LiDAR, it would spin in space and I'd get a map, I'll call it. But if it's LLM, will I get 5 Eurodolls? Will I get 1 Eurodol? This whole idea of here's an image, here's another image, what's overlapping between the images? Okay, so we can imagine an LLM giving us a panoramic description of what's in the room, but seeing what Vet did, we can imagine there being 1 Eurodol and getting either 0 or 5 Eurodolls.
So I think if you break down the acronym SLAM, simultaneous localization and mapping, you can sort of like ask what's the abstract equivalent of both. So for a regular SLAM algorithm, localization means give me X and Y where I am right now in a global system. And mapping means give me like a XY grid where all the objects are and build it up over time. So I think the analogies here would be the equivalent to localization is sort of like relative positioning. I'm behind the Yoda doll and to the left of the flower pot. So it's that kind of like more qualitative orientation or localization information. And mapping would be, to start with, here are all the objects in the field of view. 1 doll, 1 flower pot, blah, blah, blah. And then you can say things like the map is these objects and then these relations between them. So things like doll is to the left of something else. So scene description becomes the equivalent of mapping, and localization is like relative position in the scene. So
well, I think that's exactly what we need to define, because when a regular rover does SLAM, we know exactly where it is. When we do slalom, okay, let's call it slalom because maybe we'll find an acronym. It's like that joke about Microsoft and the hot air balloon. You know, two people flying in a hot air balloon, they get lost. Okay, so it's the same thing. The robot positions itself in some sense. And I'm wondering what that sense is, because yeah, maybe being in front and in back and near is the best we can do, but maybe it's all we need to do. In other words,
But even that requires some basic orientation sensor, right? At least in IMU, because
why?
internally we have like a concept of down, because there is an IMU inside us that tells us what is down.
I'm not saying you're wrong, but if we think about that rover sitting in the garage, so the floor is flat, and the rover can turn around, and that's all it needs to know.
Okay.
Well, it doesn't know if what's left and right.
So I don't think it does. So
No.
I think Myra is right here. So let me give you guys a toy example, like the simplest case I can think of. Imagine like a room-sized environment with a lot of completely unique objects in it and lots of open space between them. And at any given position you are in, you can see a certain subset of the objects. So assume that you're like excluding all occluded objects, and the rover does a 360-degree spin and says, now I can see Eurodol, flower pot, blah, blah, blah. So first of all, you've now got like kind of like non-geometric location sensing, which is like, I am wherever the location is where I can see both the Yoda doll and the flower pot, something like that. Okay, so that's the location information. And that might be all you need to do useful action. So suppose we further categorize the objects as dangerous and friendly. So back away from all things like Yoda dolls and certain other things and go towards things that are like friendly, right? I think you can do this entire thing without the robot ever knowing what left or right is, and like basically navigating entirely in object space and learning basically a mapping between objects in the visual field and action. So every location is simply known by the landmarks you can see around it. And you kind of like segment the entire map by, as you move around, you kind of recalibrate occasionally. And then, of course, you'll cross boundaries where suddenly you're from Yoda plus flower pot patch of ground to Yoda plus toy car patch of ground, right? So you'll create an implicit sort of like cellular structure in the environment with some transition graph between it.
So we spoke about something similar about, I don't know, 2 years ago, but what we didn't have is a tool which imperfectly as LLM is able to build the equivalent of a concept map. And I think really the question is how bad can it be? It's difficult for me to imagine doing it without the concept of right or left. So if we're always flat on the ground and gravity is down, it's enough to have right and left to have some. But so I don't know if it's possible to do without that. But it would be interesting to build such a map and, of course, make it out of little pieces of rovers left on Mars and hang it on our wall as art.
Yeah, and I think the left and right will implicitly get learned in the scene description to action mapping. So, for example, if the left half of the room is all dangerous things and the right half is all friendly things, it'll implicitly learn that whenever it's facing, well, I shouldn't say left or right, let's say east or west, whenever it's facing north, it'll learn an action mapping that says never go east, always go west, and vice versa when it's facing the other way. So that's learnable without having an explicit concept of left and right, which is, I still think it would be useful for it to learn left and right, but it would be nice for it to learn left and right in a paradigm where you didn't have to explicitly, like, define them as abstractions. Like if it learns a latent version of chirality, this is what we're talking about basically, by itself, that would be. Actually, a problem like this has been kind of solved by large image models, right? Like initially, they were really struggling to show reflections well. They got reflections wrong. They did not get mirror image symmetry even remotely correct. And the latest ones, including the video Sora ones, if you saw the one video which is about the view from a bullet train in Tokyo, there's a reflection of a person in the glass while looking at the scene outside. That's extremely sophisticated mirror symmetry processing. But as far as I can tell, yeah, they've probably not explicitly taught the video model anything about right or left. It's just picked it up in its general learning. Gravity as well. Like if you train a robot or rover in 2D with gravity down, and then you take it to a space station where it's like flying around, or a drone. A drone is a better example. A drone on Earth versus a drone on ISS. What would happen? It would.
What does a nauseated rover look like? Does it just stand in place? Does it start flopping up and down?
I think what would happen is it would throw away the old model and start relearning from scratch. Like if the dissonance gets sufficiently high, it'll probably discard the old data. At least that's how I would design it explicitly, I think. I mean, I got to drop off early today, prep for my next meeting. Anything else? Oh yeah, we were talking about humanoid robots a bit, right? Has there been, there's some new announcement of humanoid robots? What was that?
What was it? Figure AI got some funding from OpenAI or something. But everybody's building, and then there is Unitree also coming up with.
Didn't Amazon invest in one? I think Amazon just invested. Was it the same one?
Unitree is the Chinese company, right? So it's, I think that is what I saw last week.
Check. Oh, Amazon begins using humanoid robot in warehouse. Ooh, all right. This might be a worthwhile video to share. Hold on. Let me see if I can.
So this is what I saw last week.
Oh wait, are you sharing? Sorry, I started sharing too. Let me stop. Oh yeah, what were you sharing? There we go.
This one.
Ooh, that's pretty fast.
That looks like it's doing a karate kata.
I'd like to see it doing Tai Chi.
One of the things I've never understood with the legged robots is they are always in like a stepping cycle. They don't just stand still. They're like constantly stepping up and down. The dogs do this, the bipeds are doing this now. I wonder if there's like some control strategy that requires them to be in stepping mode, basically marching in place. Yeah, look, the dog is also doing the same thing. Oh, it stopped.
But is the mechanics of human walking is it fully understood? Like how we actually walk?
I mean, I've seen some pretty good models of it. I mean, there's nothing mysterious about it. It's like, how detailed do you want the model to be? It's like basic mechanism with some like stability and passive limit cycle type dynamics. So they're pretty solid models. But I mean, I don't know that they're that useful. Again, as with everything in these AI things, it's probably best to like just learn brute force with like reinforcement or some other scheme. But let me share the one I found just now, which is this is Amazon just started using humanoid robots in its warehouse. Just like a warehouse is a controlled enough environment and they have enough history and success that I think they can pull this off. Like to the extent
Uh,
humanoid is the right strategy, I think it's doable for warehouses at
but
least.
like I don't know why would you go with a humanoid?
If
It's a limit.
Because
It's
our
limiting.
world is built for humanoid creatures. Imagine even sitting in a wheelchair. There's a lot of things you just the wrong height you can't
No,
get
this
at.
could be done better by a quadruped, right? It could carry more weight. Why would you need a humanoid?
I mean,
Well,
there are
let me-
narrow spaces and narrow, sort of like vertically.
I mean, are we at the cusp of some breakthrough? What got us here? Why does it feel so sci-fi?
Yeah, it really feels like we are. I think a lot of it is just sort of the
I don't want to listen to Bloomberg people comment about this, but yeah. Uh, so one reason is, of course, you need manipulators as well as like floor mobility. So you need to walk from point A to point B, and then you need to lift and carry and rotate, pallets and packages and wrap them. So you need hand-like things as well as leg-like things. The question is, do you need 4 legs or 2 legs? I think 2 legs is more flexible. It can get
cheaper.
into narrower spaces. Yeah, the hardware will be
More
cheaper. The
difficult for humanoids.
what will be more difficult?
Yeah, you have to also check in the balancing, right? You are
That's
not supposed to.
solved. That's solved. I think it just needs the actuators are a little harder, but yeah, that's solved in like multiple different ways. But think of other things like humans can climb vertical ladders. They can like climb ropes. It's fundamentally a more flexible form. That's why monkeys and apes are fundamentally more agile than dogs and cats. They can climb trees. They can swing
But they
from
do
one.
walk on four. Uh,
They do, yeah. So
yeah.
I think you could have 2 more robot that could do both quadruped and biped. But in general, this is Asimov's science fiction thesis, right? And all his robot stories are based on the premise that the human environment is already there, and unless you want to like completely rebuild the environment for a new form factor, there's a lot of advantage to just
Well,
having robots that can operate in the existing environment.
the difference between a quadruped and
except
my monkey walking on four is basically the palm, right? The how the palms can fold. Otherwise, they are similar.
Yeah, and speed. The main difference, the
Yeah,
main
what
reason.
did you think about?
Yeah, what are we saying, Mayor?
I was just saying, think about the sewer system. It's a whole space, and being biped is not good. Also, quadruped is not good. Okay, you really want to have, if it's a small sewers, you want to be more like an octopus, and lean on all the walls.
Though that's actually a good example of biped affordances as well, because the manhole system of climbing down into the sewers, that's optimized for bipeds. It's like
Those
vertical
are
ladders that
biped.
go like yeah.
Yeah.
So it's built
It
for
could be
bipeds.
something like Doctor Octopus from Spider-Man.
That's, I think, overpowered. You want the minimal morphology that does the job. Oh, the other thing to keep in mind, this is relevant for rovers. Asimov's original stories, one of the justifications for having humanoid robots was you could send them to colonize other planets and like build them up in a form factor suitable for humans to follow. If you sent other things that might be better at things like terraforming, you won't be able to like build it up in a way that's adapted to humans, especially if it's extremely open-ended evolution. You send robots that are biped into a completely unknown environment, they're going to like change the environment in ways that suit bipeds if they're like doing open-ended like deep learning type approaches. So they'll very naturally invent things like chairs and ladders and other things that are suitable for bipeds. That was my version of my updated version of Asimov's thesis is that. Anyway, I got to sign off now, so we can pick up this discussion later, I guess.
Yeah, maybe we can edit today. Okay, bye.
So,
But